So welcome everyone. Thank you for joining us for the DeFord lecture series. My name is Elizabeth Catlos and I'm a faculty member in the Department of Geological Sciences at the University of Texas at Austin. We're part of the Jackson School of Geosciences, and the DeFord lecture series is our departmental seminar series. It's been a requirement and tradition for all graduate students since the late 1940s. The lecture series is named after Professor Roland DeFord, who joined the university as a professor in 1948 with the purpose of enhancing the quality of the graduate program of the department. The lecture series is supported by a range of endowments, and today's speaker is the Judd H. and Cynthia S. Walling Centennial Lecturer in Geological Sciences. The lectureship was established in 1983 to bring exceptional and distinguished lecturers to the Jackson School for the benefit of the geosciences community at UT Austin. The endowment honors Mr. Judd H. Walling of Houston, Texas. He's a 1942 geology graduate of UT Austin, and he's former vice president and general manager of Getty Company's Southern Exploration and Production Division. He was a director and executive committee member of the Oklahoma Petroleum Council and a member of both the Western Oil and Gas Association and the Illinois Oil and Gas Association. Mr. Walling was instrumental in securing the Getty Oil Company Chair, which is the first company-sponsored chair within the Geology Foundation, and it's currently held by Dr. Mark Cluse in the Department of Geological Sciences. Our speaker today will be introduced formally by Dr. Sam Moore, who is the Director of Outreach and Diversity in the Jackson School of Geosciences.
Welcome, everyone. It's an honor to introduce Dr. Rufus Catchings, who's a research geophysicist with the Earthquake Science Center at the USGA in Mountain View, California. Dr. Catchings' academic pathway is from Appalachian State to MIT to UW-Madison, and finally his PhD from Stanford University in geophysics. His research area is seismic evaluation of the Earth's subsurface, resources and hazards, and you saw the abstract to see what his talk would be about today. In addition to his time as a research geophysicist since 1981 at the Earthquake Science Center at USGA, he also served as the chief scientist from 2005 to 2008 for the earthquake hazards team at the USGA in Menlo Park. His honors include a fellow of the Geological Society of America, a Special Act Award from the U.S. Department of the Interior, Superior Service Award from the U.S. Department of Interior, and most recently, a Geological Society of America Bromley Award. More than 100, Dr. Catchings has more than 130 journal publications and reports, hundreds of published abstracts, and has advised several MS students and PhD students. Because of his depth of knowledge of seismicity, he's been a technical advisor to more than 60 federal, state, local, private, national, and international organizations. Thank you for joining us today, and we look forward to your talk, Dr. Catchings.
Well, thank you. Thank you for the introduction, Sam. And thank you for inviting me to be a part of the DeFord lecture series. First, I'd like to acknowledge that the work I'll be presenting I've done with a lot of colleagues, some of who are listed at the bottom of this slide, and from US Geological Survey, as well as the California Geological Survey, several international organizations, and just a lot of colleagues who've helped out in doing this type of research. So the title of my talk again is Earthquake Fault Exploration and Evaluation. You might not think of faults as something that you would explore for, but if you look at this picture, you see that in an urban setting, that's clearly what you have to do. So in this talk, I want to cover really kind of three areas. Talk about earthquake hazards and faulting in general, and then also cover some new methods that we use to try to find faults in complicated areas. And then finally give a series of example studies in various locations. So a few facts about earthquakes for people who are not that familiar with it. Worldwide, on average, there are about 13,000 people who die from earthquakes annually. The damage is about $12 billion annually. And as an example, for the 2011 Tohoku, Japan earthquake, the cost was about $235 billion. And more close to home, there was a magnitude 7.1 Ridgecrest earthquake in 2019 in California. And that earthquake cost about $5 billion, even though it was in a rural area. And that's largely because it was on a military base, and there was a lot of damage to the base itself. And that's where most of that cost came from. In the US, damage is typically about $4.4 billion annually. And contrary to what a lot of people believe, earthquakes are not just a California problem. 42 of the 50 states have some form of earthquake hazards. And as you may know, the state with the probably most earthquakes in the last few years have been Oklahoma. But you being in Texas, many of you in Texas, you probably know that there are quite a few earthquakes in Texas now too, and those are, both Oklahoma and Texas are largely due to induced seismicity, but they don't occur in a vacuum. There are faults there as well. California clearly has the highest risk. That's because with close to 40 billion people and many, many active faults, that becomes an issue. So as I mentioned, induced earthquakes in the central US, this is kind of a map of it. You see that the number of earthquakes really ticked up starting around 10 years ago. And you can see that they peaked, they start to come down quite a bit, but still there are a lot of earthquakes, and that's largely due to induced seismicity. But you have to look at the other areas too. This is the northeastern United States, and these are maps. This is just something I pulled off the internet, and you see that there are lots of earthquakes there. And many of them are small, but over time, some of them could be quite large. And there has been a history of fairly large earthquakes. For example, even in the New York area, New York City area. But many of these places are covered by sediment or urbanization, so it makes it difficult to understand where the faults are, how long are the faults, how they're connected. And so this is one area that we've focused on at USGS to try to understand that. And I'm going to use the San Francisco Bay Area as kind of a test area, or an area that I first talk about for earthquakes and fault hazards, because that's, first of all, where I am, and we do a lot of work related to that. So if you look at this map or this photo to the right, I don't know, I hope you can see the red lines on it. Those are the historically active faults in the San Francisco Bay Area. And San Francisco is here. And this is the San Francisco Bay, and most of the urban population lives all within this. And you don't see a lot of red faults in there. And that's not because there aren't active faults there. It's because they generally are not that well mapped, just because they're of urbanization and sediments. Now, the important thing here is this is the San Andreas fault running here. It's a very long fault. So generally, the longer the fault, it infers you can get a larger magnitude earthquake from that fault. For example, the 1906 San Francisco earthquake was magnitude 7.9. Many of the other earthquakes that have occurred on these other faults have been smaller, but still very destructive earthquakes. So the question is, are any of these faults connected? Could it be a long fault? And that's one of the things that we try to answer. And are there other faults? And the answer to that is yes. There are plenty of faults, as you can see. If you just look at the offshore version, I'll go back and forth here, and you see that lots of faults out there. What you don't see is there are lots of faults in here as well in the interior area. And that's because they're dark colored. And so if I bring those up and as yellow, you see the entire area is kind of riddled with faults. But how are these things connected, and what's the hazard? We can get some idea from the earthquakes that occur on them. And if we look at that, this is the seismicity shown in the yellow dots. And we can see a lot of those historically active earthquakes. Faults host a lot of earthquakes. But there are places where there are lots of earthquakes that there are no map faults. So we really need to kind of understand this problem in some detail. And the other problem is a lot of faults that are potentially active that will become active, they just don't have earthquakes at the moment. And so we really have to try to pin down this problem. And I'll show you why is because if we look at the population base. Now, in 1906, this is what the population centers looked like in the San Francisco Bay Area. There was about 650,000 people, and there was not a lot of population exposure. You can see the San Andreas Fault running through here fairly well. But as you saw from that previous picture, there are lots of faults out here in the population area. So if we look at, fast forward to 1990, a year after the Loma Prieta earthquake that we had here, you can see the population has grown tremendously, and it's on top of all kinds of faults. Fast forward to almost to today, this is what it's expected to look like in 2025. Again, you can see that the population base is all over many of these faults. So we really need to know not only about these faults, but the connectivity of these faults and what kind of maximum magnitude earthquake are they can they possibly generate. So again, here are my questions. Where are the faults? What are their lengths? You know, the maximum magnitude and connectivity, and how can we determine this? So one way is just wait for an earthquake. Now, this is from, I think, New Zealand, a photograph. And this is incredibly bad luck. Look at this whole area here. And out of the entire area, wide open area, this house just happens to sit on top of a fault. And that's one of the things that we want to avoid, particularly in urban areas, putting building and important infrastructure on top of faults. But we need to know that before something like this happens. So the methods that we've typically used are in exploring for faults is what generally everybody else uses, geomorphology. But the problem with that is it's difficult in urban settings because urbanization has often stripped away a lot of the evidence. You could have high sedimentation or erosion rates in places. And then there's the problem of blind faults. Blind faults don't come to the surface. So you're just not going to see them with geomorphology studies. Trenching studies are kind of like the gold standard, but first you have to know where the fault is to trench. And it gives you good information in the upper few meters, and that's critical. But again, it's difficult in urban settings just because it's hard to do a kilometer-long trench through an urban area without tearing down a lot of infrastructure. And it's also expensive and time-consuming. Boreholes and CPT, they have the same issues. Now, we can also look at earthquake monitoring. Earthquake monitoring helps. It helps us know what's active at the time, but not all faults are active at any given time. And it didn't give you very much information at shallow depths, because earthquakes just don't generally occur at the surface. So what we really need is some way of really determining where faults are in the near surface. And over on the right, I list a series of methods that we've used or that I've used. One is guided wave exploration, and I'll explain about that later. But it's an excellent tool for finding individual fault traces, which is often what we need. And this PGV method works in almost all settings and is fast and relatively inexpensive to do. Another method that we use often is Vpvs Demography. Now, the VP part of it is not that ideal at shallow depths because groundwater and other features tend to obscure faults. But VS is good at all depths. And when you use the ratio of the two, Vpvs, it can be a very powerful tool in locating shallow faults. Now, we've also used MASW, or multi-channel analysis of surface waves. And that's a very powerful tool in the right place. However, it's difficult in complex settings. If you have elevation changes and things like that, which you often have over faults, MASW is not the best tool. Now, reflection imaging in layered basins is just a beautiful tool, but it's not that good in complex settings. And there are also other methods like geophysical methods, GPR, resistivity, gravity, etc. Those all have limitations, especially in urban settings. And I'll show, for example, here. This is some pictures along the San Andreas Fault. And you can imagine trying to do a lot of those types of studies here. Reflection imaging, which is just a beautiful tool, just would not work here. So a more effective tool are really those first two that I mentioned, PGV of guided waves and Vpvs tomography. So I'm going to start out explaining a little bit about guided waves and the PGV of guided wave method that I use. So again, I want to mention the benefits of it. It's really cost effective, it's fast, it's highly accurate, and it can be done in most places. And so let me give you a little bit of an explanation for those not familiar with guided waves. Now, guided waves have been around for a while. People discovered them several decades ago. And I'll kind of explain a little bit about how they come about and what they are. So if we look over to the right in map view, you see this kind of beige color. I have this cartoon as a fault. And if there's an earthquake on that fault, and we put an array of seismometers across that fault, we will have something like this. So here it is in cross section. You have high velocity rocks on one side, high velocity rocks on the other, and then you have this fault zone right in the middle. If you look at from this seismometer array, you'll see your normal P wave, your normal S wave, but then over the fault zone, you get this really slow moving, high amplitude guided waves. It's essentially, some people refer to it as a trapped wave, excuse me, or it's really a wave that's just bouncing around inside of the fault, and it generally generates very high amplitudes. And so it's really a waveguide, and we see this on almost all faults. We can use that to our advantage. Now, here's a numerical study from 1996 by Leon Vidali. And let's say that you have a fault in the subsurface like this. It looks like a Y with equal strands on either side. You take this array of seismometers, it's been flipped on side to show, but if you put it across there, you get high amplitude guided waves on each branch of the fault coming to the surface. If one branch coming to the surface is thicker than the other, you get a higher guided wave, a bigger guided wave on one side relative to the other. If you have step overs, guided waves become somewhat diminished, but you still see them. And as the fault becomes separated in the subsurface, eventually you get no guided wave at all. So this tells us two things. One, if we see a guided wave from a source, we know that between the source and the observation point, the fault is connected. It's one continuous fault in one way or the other. The other thing that I began to wonder at some time ago was if having such a situation like this, rather than just looking at the guided wave in waveform, it may be very much more simple to look at it in terms of peak ground velocity or peak amplitude. And I did a few tests, and what I found was that, yes, indeed, if you get this peak right above where this fault comes to the surface. So, excuse me, this can be very useful because a typical guided wave can be 2-3 kilometers wide, that zone in the waveforms. And it's hard to pinpoint where individual faults or fault traces are coming to the surface. But using this PGV method, you can pinpoint it fairly well. And I'll show some examples of that. Now, here's one example from our work in Napa, where we used the standard waveform method to identify the guided waves, the P, the S, and then the guided waves here, that's big amplitude. And we also used the PGV of guided wave method. And you can see that it peaks very nicely where we know we need to look for a fault and tell us something about the width of the fault zone. It also identified additional faults out to the side, and I'll show that in some subsequent slides. So I'm going to show just a couple of examples along the San Francisco Peninsula. Excuse me. So following the 1906 magnitude, approximately 7.9 San Francisco earthquake that largely destroyed the city, and the city of San Francisco is shown here. This is the Bay Area and the urbanized area. There are a series of reservoirs along the San Andreas Fault, and those are used as water storage, and it provides water to the city of San Francisco as well as many of the approximately 7 million people that live in the Bay Area, or 8 million now. So in 1906, Schuessler was an engineer, and following the great 1906 earthquake, he went out and he created this map, and he mapped out the fault strands in detail. This was a water intake system, a well, and the shearing of the fault turned this from a completely round thing into a sheared feature. It severed lines and things like this for the intake system. So we had this map, and in 2008, the San Francisco Public Utilities Commission asked us to, well, can you tell us where each of these faults are? Because we want to, we know here, but all along this reservoir, we want to know where the faults are so that we can retrofit our intake system to guard against future large earthquakes. So they lowered the reservoir as they were doing this for the first time in decades, maybe the lowest since maybe 1906. And so I took advantage of that by putting out a seismic array here, very detailed, only 60 meters long. And I knew where these faults were. And rather than waiting for an earthquake, I generated a small shot here, seismic energy inside the known fault zone here, and then watch it propagate down. And to see if I could actually locate these same things that he had mapped. Now, again, this is San Andreas Lake, San Andreas Reservoir, and it is the namesake of the San Andreas Fault. Even though the fault runs about 1,100 kilometers all the way from Northern California down to near the Mexican border, it got its name here just because of this rupture in 1906. So this is the waveform, and the waveform doesn't tell me an awful lot, but I can see guided waves, I can see P waves, I can see S waves coming through it. I can see an air wave. But then I plotted in terms of PGV. And this below is a tomography, a refraction tomography S-wave model. And what we see is that always along fault zones for S waves, we get these low velocity zones, rather extreme low velocity zones relative to everything else. This is rock that outcrops at the surface, and it appears that there's a fault cutting through in this area. So we were able to locate, this is the fault, the main fault mapped by Schuessler, and we get a peak here. This was another one, the projection of it, it stopped about 5 to 10 meters just before this. And this is extreme small detail stuff. So there's another peak there. And this fault, this third fault that he mapped here, and we have it coming, a fault coming out like this. So whenever the fault dips, it's a couple of meters off, but not very far. So we get these three peaks just as he had mapped them. So we felt like the method is working very well. So following that, our paleoseismologists also wanted to trench the San Andreas Fault so that they understand the repeat history. And it's important that they look at each and every strand of the fault. If there are other traces in either direction, they need to know that. And it's not practical to have a very long trench here, or it's very inexpensive. So knowing that this method has worked out in numerous places, we put a seismic line here, and we put, again, a source inside the fault zone, and we look for guided waves along here. And if we saw a lot of guided waves here, we know that there's an additional strand out here, or in any direction. If we only saw it here, then we know that's the main fault. And when we look at that, in fact, this is a VPVS model along there. Again, we get an anomaly here where they knew the fault was. This is where they were going to place the trench. But if you look at the PGV of guided waves, you see it just kind of goes off the scale right there at the fault. So that's telling us that indeed this is the main fault. We also identified a small fault out in this area, which they were not interested in because they determined that's a relatively old fault. So they knew they did not have to trench all the way out in this direction. So it became a very valuable tool where they could just focus their studies just in this area. Now, also print some examples from Napa in 2014. There was a magnitude 6 earthquake. Napa is the wine country of San Francisco area, and it did a lot of damage. So there was an earthquake there at magnitude 6. It occurred down in this area to the south part of this map here. And there were ruptures about 12 kilometers long. And you see that the ruptures were really spread out about 2 kilometers wide to the middle area here. And it appears that they were coming together, and there was into maybe one strand up in this northern area. So we again did a guided wave. They wanted to trench a year later. They knew the strand over, if we look to the figure on the right, they knew the main strand was to the southwest, and there was another strand just not very far from that. And when I got out to do the study, the owner of the property notified me that, hey, there's another fault just to the northeast here that ruptured during the earthquake. And I said, okay, well, maybe I should spread out this array some to make sure we're getting all the strands. So when we looked at the PGV of guided waves, here was the main trace, trace A, the southwest rupture. And you see it's a very high. And then this is that second trace that ruptured that we knew about. Trace C was the rupture identified by the owner of the property. And as we went out, there was another trace, trace D and trace E. And had I continued the array, there are probably additional traces out there. Traces C, D, and E probably did not make it to the surface. And there are probably additional ones further out. So this fault zone was not necessarily coalescing, becoming one strand to the northeast like we had estimated, or that geologists had thought. It's simply that it's in the subsurface. So it's a very wide fault zone again. And in this particular area, when they actually trenched it, we knew this was ruptured. It ruptured the surface in 2014, and we went back in 2015 and did the paleoseismic study across there. There was no strong evidence for a fault at all. although the guided waves clearly show that there's a fault there, the rupture from the year prior showed that there's a fault there. So in some cases, this method can be even more reliable than, say, the paleoseismic method. So when we look at it in map view, yes, there was this trace A, there was this trace B, and then there was trace C, trace D, trace E, and if we had continued to fault, I suspect additional traces out that way. So all of these faults are connected at depth because we put one source in and we can just see they all light up in terms of PGV of guided waves. So another example from NAPO that we did, as soon as the earthquake occurred, we deployed a whole series of instruments. And then this particular area, Napa, is here near the center of this rectangle or square. And again, you can see the active faults on here. But this earthquake occurred on what everyone thought was an inactive fault. And if we look at the rupture, this is the rupture here. And you see that it's not very long, it's about 12 kilometers long, but it generated a magnitude 6. And the question is this fault connected to something else? Is it a continuous fault, or is it just this small thing that we have to worry about? And we're going to see a lot of that. So one of the ways of looking at that was, again, I went out, again, the rupture is shown here in red, and I put out a series of rays, one above the surface rupture, the other kind of in the middle of the surface rupture, and then one far to the south. And we just recorded earthquakes on those, because we wanted to know, there are faults mapped to the south. I don't know if you can see this, the thin yellow line. It's on projection to come up to this fault. And there are faults to the north that project. So I want to know, are these things, is this a much longer fault and just part of it rupture, or is this all we really have to worry about? So again, my suspicion was the yellow fault, the thing continued somewhat like this. And we started to look at aftershocks from that along these guided waves and guided wave arrays. And we could clearly see the main rupture or the projected rupture to the north here. The faults, the rupture stopped here, but we could see this area here. Clearly, there's a big guided wave coming through, and there are some additional faults out to the east in this area as well, which we also picked up. And then if we looked at some of the arrays further to the south, again, this is the rupture, and we can see, again, we get these peaks just about over the rupture. And then there's also faults further to the south. We just continued to look at a series of aftershocks and see how they propagated on this array, that array, that array. And that finally, we could see guided waves from all of them. And remember, a guided wave, if the fault is not continuous, you will not get a continuous guided wave. So we determined that the fault is somewhat like this. It's quite a large fault system. Just in this area alone, it's at least 110 kilometers long, not the 12 kilometers, 10 times longer than what ruptured. So this could generate a very large magnitude earthquake. But again, faults had been mapped to the north and faults had been mapped to the south. And it appears that this small rupture continues to the south. It appears to link up with the Calaveras fault. And to the north, it links up with another fault. So the whole fault system appears to be quite long. Hundreds, probably a couple of 100 kilometers long or more, suggesting that it can give a very large magnitude earthquake. So that's one of the benefits of really kind of tracing these things out using guided waves. So PG of guided waves, we find it as a highly accurate method. You can explore the entire fault zone looking at individual traces or or just the entire zone. And it can be used in most places, whether you're in an urban setting or rural setting. And it infers, what I didn't get into is something about the ground shaking. You can see that those PGV values are often 5 to 10 times higher than the background S wave. So it can, in those zones, it can generate some very, very strong shaking. And using this method, it can show the connectivity of the faults. So the guided wave method works well. And that's when we know where there's a fault trace or we record an earthquake or something like that. But in some places, we just, it's a blank slate. We know nothing about it. But if we have the suspicion, we can also use these tomographic Vpvs ratios. And again, you might say, just use reflection. And again, I point out here that reflection and most other methods just simply won't work in areas like this. So we fall back to these alternative methods. So how does it work? Essentially, if we look at the P wave in the very shallow section and saturated materials, the velocity tends to increase when you have water saturation. The P wave velocity increases, whereas the S wave, due to shearing, actually decreases. So if you look at those ratios, you can get very high ratios. And even if you don't have saturation, the P wave will decrease a small amount, but the S wave will decrease quite a bit. And so you still get a high Vpvs ratio. And here is an example study using that, again, across the San Andreas Fault. We had a profile across here is 1906 rupture. And these are some data from that, just a couple of shots. We have a lot of shots in these particular studies. We maybe shoot every 5 meters, sometimes even closer, just to get the real details. And if we look at this tomographic image that we get from here, you notice the P wave is very high because this was basically a sag pond area, and we get saturation. So the P wave gets to be high. S wave, however, is low. And just on that basis alone, I was kind of making an estimate of what I thought the fault looked like. But when we look at Vpvs ratios, this shows it quite prominently. And the ratios get up to 10 in this particular case. And the interpreted fault was just wherever we have these highest areas. That's the S wave is lowest, the P wave is relatively high or stable, you get these high ratios. And when we submitted this for publication, one of the reviewers pointed out that, hey, there are probably nearby trenches. Why don't you see how your fault interpretation matches with the trench? So we did that, and here is the actual trench, which is about 1 kilometer north of this study. And the red shows our interpreted fault, and the black shows what they determined from the trench. So it matched very well. So we find that from this and many other studies that it works well. Here's another example study. We were asked to do profiles all along this reservoir so that the intake system could be protected. We knew about the 1906 rupture, and we also found an unknown fault here, which I'll show. Now the P wave, there's nothing particularly dramatic about it that would tell you anything about a fault. The S wave, you see relatively low velocities in certain areas. But when you look at the Vpvs ratio, you get these highs around the 1906 rupture, and we found another out here. The San Francisco Public Utilities Commission, which owned the property and which wanted to know about the faulting, actually wanted this whole thing to trench to test out the method. So they trenched about a 200-meter long trench in this area. And this is a picture from part of that trench. And they found 2 faults. They found a 1906 break, and they found this fault here. So it showed that the method actually worked very well. So using this Vpvs method, you can basically identify faults in places where the rocks are massive or deformed, or otherwise places where a lot of techniques will not work. you tend to get the highest Vpvs ratio when you have saturated zones near the surface, but that's not a requirement. For faults that are groundwater barriers, you can get high ratios on either side, but you can also get an anomaly in the middle. There will always be some type of anomaly. And even at greater depths, when velocities get above about 2,500 meters per second, you tend to get VP low velocity zones as well. So we use these methods and we combine those two with other methods wherever necessary, and particularly in urban areas, to try to figure out where the faults are. So you can just look at these pictures and figure that trying to locate faults is a bit challenging in this type of environment. So one of the places that we tried it out was in Beijing, China. This is kind of like a photo of the Beijing area, the greater Beijing area. The yellow lines show the freeways essentially circling the city. But there's one fault here, which I will not even attempt to pronounce the name of it, but I simply call it the HCGLY fault. That fault here was having some quite fast slipping. And we wanted to have a look at that and see if we could trace this thing out. It's not very visible at the surface except for what it's doing to buildings and things like that. So if you look in the lower left side here, you can see what it's doing to the road. You can see that this fault's coming through. It's coming through this building. It's quite a long factory building, and you can actually see where it's just ripping the factory apart. And this is another view further up, so you can actually trace. So we know the width of the fault zone just from that building, or the part that's moving. And so we did a guided wave survey and a tomography survey over it. We get the classic low velocity zone over the fault. But we also get these high PGV values, basically along the faults that correlate with where we're seeing the damage in the building. So that worked very well there. We then went away from the building further to the northeast and traced the fault. And we found that this method, once we find one location, you can just simply trace it out. And then in Los Angeles, Los Angeles is a complicated area with about 19 million people, second largest urban area in the US. And it's got numerous faults, and a lot of them are blind faults, which we know of. And California has this peculiar law called the AP law, or Alquist-Priolo law, which prohibits building on known faults. But you have to know where the faults are. And so in a lot of cases, the people who actually own the property, they have to just have somebody come out and verify that there's not a fault there, if there's any suspicion at all, which can be kind of expensive. And that's usually done by trenching. Excuse me. So we started out looking at this Raymond, Hollywood, Santa Monica fault system that runs along the northern part, which can generate an appreciable earthquake or the whole thing to rupture. And we wanted to know where each individual strand of the fault is. So we first started out, there was a trench with a known location of the fault, and we put out arrays along the city streets here. And there's a major 4-lane road, which is really maybe like a highway, 4-lane street with a lot of cars coming through in the middle of this, and we knew it would be a problem. So we just repeated our source for about an hour and then looked at the PGV of guided waves. So we were able to locate what we thought was the Raymond fault and various splay faults going out. Now notice that the busy street shows very little or nothing because we repeated the source so many times that it tends to stack the energy in and stack out the noise. So Again, on the left is where we identified faults just strictly based on the guided waves. And here is a 1928 aerial photo that consultants use, and based on what they could see from the photos, from some drilling and some mapping, they independently determine the fault locations. And here are seismic lines again, over on the right side in blue. You can see the arrows pointing out where they say the faults are. And then that same thing, fast forward to 2020 or so. And you can see that, in fact, they correlate very well. This one is about 10 to 15 meters off, but we think our location is actually better than their location. So we continued that to move across. So we looked at additional ones further to the southwest. And again, we saw these prominent peaks in various places where we identified fault zones. And this one prominently, and about a couple of weeks, 2 or 3 weeks, maybe a month afterwards, they actually trenched this area. And this is a picture of that trench. And again, this is the only place where they found faults that correlate with that. So again, showing that the method works very well. We continue to trace out these faults and locate them in the city of Hollywood. Again, we have that AP law situation, and they wanted to develop some of the property there. And this is a major development site where they wanted to put high rises, lots of high rises. And this is what the California Geological Survey had interpreted as faults going through the yellow lines. This is where they actually had found, had trenched a fault. So we put out our arrays here, and we wanted to see where exactly were we seeing faults. So again, the development area is shown here in the magenta. The place where they had determined that there was a fault is here. The cyan lines are our seismic lines shown here. And so the yellow line shows basically where we determined this peak in the PGV. We located the fault, I think, very well. And then along this line, we did similar studies. We used a combination of things, and we determined the faults here. So the California Geological Survey, based on geomorphology, had actually located it fairly well. This one was only about, this first one, I don't know, 20 to 30 meters off. But still, that's very important for a property owner, 20 or 30 meters. So we could pinpoint it. And we thought they were very, very close here, maybe 5-10 meters off. And it does go across, apparently goes across this development site. We also looked at Vpvs, BNS, and we also get these high prominent Vpvs ratios underneath the fault zone here. It doesn't come all the way to the surface because the groundwater table is quite low in this area, but we do still see the relative highs. We also used MASW, multi-channel analysis of surface waves, and you can see it does give us a prominent low velocity zone, both for the Rayleigh wave as well as the Love wave over the fault zone. In combining all these methods, so we were fairly certain of where the fault was located. Now, they had done a bunch of boreholes in this area as well as CPT. And the consultants who did this came to the conclusion that there was no fault. This was a paleo channel, and it's not something they really had to worry about. But from our studies using multiple methods, I think we used 14 different methods here, and they all indicate or are indicative of a fault here. So we felt fairly comfortable, fairly certain that there's a fault there. And this is, we continue to trace it out. And again, we think the fault comes through largely as the California Geological Survey had anticipated it. We then went to the city of Beverly Hills and did the same thing. looking for the faults. I won't go into a lot of detail, but essentially put out an array. This is the Newport Inglewood fault, but then there's the Santa Monica fault coming across. And we found a whole series of peaks along here, suggesting there are multi-strands to this fault. Now, this is important because there's a subway system being put in. And this subway system, you notice in magenta here on the right side figure, has a prominent bend in it. And it was put in there to largely avoid what they thought was a fault system coming through. But in fact, you can see where our cyan line or our seismic line, it appears that they are putting the subway system right through the main part of the fault system. Excuse me. So for urban investigation, both methods, the guided waves and the tomographic VPVS, works extremely well. And especially when we combine it with other data. I didn't show some data. We do have some reflection and other methods applied as well. So I want to give one final study, and this is at magnitude 7.1 Ridgecrest in 2019. This is a widely distributed fault, and as I mentioned earlier, this area is largely rural, and it's a big military base here. And when the earthquake first occurred, we went out and we put out a lot of arrays along the faults themselves. Now, this fault is interesting because it first started out as magnitude 6.4, and it ruptured from northeast to southwest. And then a day later, there was a magnitude 7.1 that ruptured southeast to northwest and also in the opposite direction. So these two faults crossed each other actually within days. So there were a lot of questions about that we thought we could answer using these arrays that we put out to monitor the data. We recorded about 30,000 earthquakes over a period of 2 months. Now, with these data that we acquired, some of our colleagues from USC also generated tomographic VPVS and VPVS models, and they were able to relocate, instead of 30,000 earthquakes, about 95,000 earthquakes. So that was the power of having many more seismometers out and using those. But we wanted to look at the fault zone itself and determine with this $5 billion worth of damage and the neighbor is going to rebuild, we wanted to see how wide was this fault zone and what was the damage. So I won't go into a lot of details, but this is kind of a fault. The yellow in this top figure shows the ruptures as mapped by our geologist, and the cyan shows the lines that we put across there, the guided wave lines. And in fact, if we look down to the southwest, we recorded an earthquake that was about 50 kilometers away from that in the recording arrays here, and we looked at where the guided waves occur and where the surface ruptures occur, and they match very well. We also see some smaller peaks here, suggesting that there are some faults that didn't quite make it to the surface. So this is kind of a continuous wide fault zone. I estimate that it's probably on the order of 5 to 6 kilometers wide. And we looked at the same thing, the crossing fault. Given that the last fault was northwest-southeast, that should have maybe cut off the guided waves from going from northeast-southwest. And we looked at that. But again, we see the prominent guided waves in the same place as they were mapped for surface ruptures, except for one. One did not show up. There was a previously mapped fault out on the northeast end. That did show up. So it's a little bit of a mixed result, but overall, we got the same result that they got from mapping. And then we looked at some other faults from earthquakes from the south going north, and we see the same thing. Wherever there was a map fault, we get these prominent high PGV values. And then what we wanted to know from that very same earthquake that was propagating along the North Ridge fault, was it doing anything along the Garlock Fault, which is a major fault in Southern California. And what are the implications for that? And indeed, we see exactly where it crosses the Garlock Fault. That's exactly where it's been mapped. That's where we get these prominent peaks. There are also apparently some strands out to the south of that, which have not been mapped, but I don't think it would surprise anyone that there are additional strands out here of a few hundred meters. So for the Ridgecrest observations, for a kilometer-wide fault, we see multiple surface traces. The guided wave propagates across orthogonal faults. It doesn't seem to matter which rupture sequence there is. We get long distance propagation. Now I should mention that that 50 kilometers of propagation that we saw on that first slide, people had previously thought that guided waves only propagate maybe 10, 15 kilometers. We can clearly see that they propagate very long distances. And we are getting propagation from the Ridgecrest Fault onto the Garlock Fault, which has some implications for triggering also. So overall conclusions, there are lots of active faults and earthquakes in the US, and it's a problem for most US states. It's a problem for many places worldwide. Laterally tracing and locating these faults is a real problem, especially in urban areas and places with a lot of sedimentation. And not all faults have ongoing seismicity, so you can't rely on seismicity to tell you where the active faults are. What's needed is a robust, reliable, non-invasive methods, and we find these two, PGV of guided waves and Vpvs ratio mapping, is very good at locating faults in the shallow subsurface. And these new methods allow for a better characterization in terms of locating the individual traces, evaluation of the fault length, the connectivity among faults, and estimating the maximum magnitude earthquake that you're likely to get from a particular fault. And just in general, overall better characterization of the fault zone. So thank you very much, and I'd be happy to take any questions.
You want to close it out, Liz?
Yeah, I think we're at the time. So thank you so much for coming. Learned a lot. I'm actually in San Mateo right now, so now I'm pretty freaked out. We'll be telling my parents all about faults in this area. But yeah, we really appreciate it. It was a wonderful talk, and thank you so much. And please come see us again Thursday for another speaker who will actually be talking about Mars, and maybe we'll hear about Mars quakes at that time. But okay, thank you. I'll end the meeting now.
Great, thank you.
Pam.